Okay, you probably remember that one of the pieces of the derivation of Lagrange's equations, the rule that was against having any velocity dependence in a potential was very strict. That is, if you did have that, then the whole thing broke down. Well, today we try to remedy that, and you have to, in order to do a Lagrangian of electromagnetic interactions. So when we do this, we're going to be having to work with a vector potential as well as a scalar potential, and that's the way you get out of that problem. So we'll still require that the scalar potential not have any velocity dependence, but the vector, it's all velocity, it's flow. Okay, as we saw when we looked at the complex variable sort of toy model for vector scalar potentials. So we've got some technical work to get through this, and some mysteries will remain after we're done with this, but the basic algebra, a little complicated, but I think very important because, well, it's what we see with. It's very much a part of our physics life and action. Now, one of the things I have to help understand that is this machine that's sitting there, which I made when I was at Georgia Tech. This is a mechanical analog for a cyclotron, and we'll play with it. But in case it breaks down, which it does, it's not engineered to a T. I have lots of videos that we can use for quantitative purposes, and that's what we'll be discussing down here. But it occurred to me just as I was putting this together again today that the mechanics, and all of this involves trajectories that are various kinds of cycloids. I thought it'd be better if we go toward the end of this lecture and do the mechanics, and that's what this stuff is on the sideboard here, right off the bat here. And the reason for that, first of all, is basic sophomore physics. You've had it, but we're looking at it with a little bit of geometry added. But also, the mechanical analog depends on this. So I'm going to jump ahead here on this screen as well and get down to basically the flying sticks. You can see a picture of that. And this is something I'm asking you to do in your problem sets as well. So we're going to zoom through this lecture until we get to the section describes the mechanics, but this right here. So what I'm doing here is setting up in as clear a way as possible what happens when you have a stick sitting in space, no gravity or anything, you're in an inertial frame, and you go up to that stick and you hit it somewhere. Okay, you get a very different set of curves depending on where you hit it. The only thing that would be simple is if you hit it right on the center of gravity, then it would just take off in the direction of the hit, like that. But any other point on that stick, and it's going to rotate as well as translate. So this is where we think of a wheel rolling on an imaginary road. That's the picture that I want you to get, that makes this dynamics that we're seeing here. That's a qualitative picture, but it helps to have that in order to make the formulation of this something that you can reproduce, hopefully yourself someday later when you're teaching. Now, the idea of hitting the stick at a certain height above the center of gravity lets us quantify the fact that you've given it some linear momentum. That's whatever, however much momentum that hammer has. It will be this thing we call Greek pi for linear momentum. But at the same time, you gave it some angular momentum. And this isn't something we've covered in great detail. We will do more about that when we talk about orbits and things like that. The interplay between translation and rotation is a very deep one that leads into special relativity, quantum mechanics, all sorts of things. But for now, it's just these two numbers we have to deal with. And there's really one number here. You gave some momentum, and then at the same time, depending on the height above the center of gravity, you gave it some angular momentum. So the question is, how much angular velocity does the thing have, and how much linear velocity does it have? And that's all there is to this little piece of classical mechanics that comes out of sophomore physics. Okay? So I want to make sure we go through that, because I'm going to use the same construction to build the cyclotron orbits of a crossed electric and magnetic field. Okay, and that's what this crazy classical analog of a cyclotron will be demonstrating. So, first of all, let's remind ourselves of what's the moment of inertia, the rotational inertia of this thing, the integral of the density of the linear density of this rod here over r squared. And it gives you the r cubed over 3. That's L, the length, this length at first here, cubed over 3. And then mass is rho L. Now that would just be one half lever, but it isn't going to change this formula here if I put another half lever here that's the same length, because then the mass is twice, and I take the 2 back out of the equation. And I could put a whole bunch of them here. If they're all the same, this would be the equation. In either case, the mass would just keep getting bigger and bigger every time you stuck another lever on it, right? Okay, that's just a minor point, but it's one that's worth having. Okay, let's get all this stuff on the screens here. This is where we figure out the velocities. And I'll go ahead on the screen down here as well. Okay, and then we want this magic point that stands still. That's what we're looking for. And that's what we'll be looking for when we do the analysis of the E cross B, the Hall effect mechanics is what we're talking about here. And we're doing a lot of Hall effect stuff down other labs in this building, so it's worth getting chummy with this kind of mechanics. Now, here I'm just saying, okay, if I angular momentum here, the angular velocity rather, this lambda of angular momentum that we've got here, h times the linear momentum divided by this inertia that we've just calculated, okay, for a stick, that's what you would get for the angular velocity. And then this should be also equal to, this is after all h, it's not Planck's constant, this is height, okay, but h times pi over I is what we're really talking about here. So with that, I can figure out where this magic point is, where the speed, that's the distance from the center of gravity to, here just call it little p for radius, p omega due to the rotation of this thing, just cancels the translational speed, and the translational speed measures how fast the center of gravity moves, you see. So these are time pictures of this stick that's been hit. So I think it's worth knowing that if you're in empty space and you have an object, this is what it does. You hit it, it does something like this, no matter what shape or solidness it has. And later on we'll talk about solid figures, but this is the very first thing to know about that. So there's cycloids all over the place, right? That's a really common, and it's not just the cycloid, say, of the outer edge here. That's a curlate cycloid, sort of curls around. But the green one here comes down here gets infinite curvature right at that point, and then pops out of that with infinite curvature the other way, and continues its way up to here. So there's the ordinary cycloid that you've been working on in your homework. All the rest of them are attachments. Then this is perlate cycloids outside. They're prolate cycloids. One of them that's really close to the center of gravity kind of looks just like a cosine or a sine curve. That's the yellow one, right? Okay. So these pieces of geometry are part of all of the motion, classical motion. And they are generating wave functions. Remember, when we do classical mechanics in that sort of combined a whole bunch of motions with the similar initial conditions, we get that. Anyway, the idea is to just solve for this magic distance right here. Okay. Now, we've been talking about dynamics of levers for things like golf and tennis and baseball. It's very nice if you were holding the lever at that point. If you're holding a lever at that point and something hits it, or you're moving it in order to hit a ball or whatever, okay, hitting it in the proper place is called a sweet spot. On a tennis racket, the sweet spot is pretty nebulous. They've designed a racket so it is error forgiving, but baseball, you really have to hit, and of course a golf club you can't miss, or you just miss the ball entirely. But the idea is then that what happens is what you would feel if you think about it, is you feel the thing you're holding not go this way or that way or that way, you feel it to second order pulling out. And remember, that's what the cycloid does. The green cycloid curve that is like this one, okay? There's another one that I haven't drawn here, starting right at this point here. So it's just, something to observe, something to think about for these. In any case, making these equations, just finish this whole board out here. I think that's what we're after right there. In this particular case, the formula for the percussion radius, okay, that's center of percussion point, COP, okay, that has no velocity after the hammer has made its entry of momentum, both angular and linear. And in this case, that's the formula that gives you, in terms of what you've already known, you presumably know the height that you hit and the length of the lever that you have. Okay, so I've got a problem I've given you to work that out just for the fun of it, and then go ahead and draw a particular family of cycloids that goes with this. Okay? So, this particular end, that's the end of this lecture, although the next step will be, and we're really getting low in our things, we're going to the pool hall and figure out why they put the bumper at a particular height. How many people have seen what that is? Have you seen that in a course anywhere? How could they leave that out, right? What do you do after the physics class? Go down and shoot a whole pool, right? Okay, well, there's a reason for putting this bumper at a particular height. We have time, we'll finish the discussion of that. But right now I want to get into the hairy stuff that we have for today. So I'm going to back the lecture all through all the stuff we're going to do today to the very beginning, where we talk about just a basic idea. I should point out we have some new stuff on here. If you want to play with a complex variable thing, we can start to do it a little bit right now. In any case, if you are going to be a teacher in physics, you're going to be teaching about the V cross B force, right? And the question is, how do you remember? Well, there's a thing called the right-hand rule, but what do you really mean by that? And I've added something to that. The right-hand rule is obtained by taking the right hand. Now, it used to be that the right wing of the politics was the FBI. It isn't true anymore. They're trying to get rid of the FBI. The right wing is trying to get rid of the FBI because it's discovering that people are doing bad things. So, in any case, let's just pretend it's like the old days when the FBI was the right. So you take your right hand and you write FBI. And then you make a gun, which is, most of the FBI agents have to learn how to use one of those things, right? Okay? But you hold your fingers like this, okay? So I've got F here, I've got the B field here, and I've got the I of the current, that's positive current, right there. How could you go wrong? Okay, so this is what you check when you see what is happening to a charge that is being moved through a B field. Now we're going to do all the algebra that goes with that. Okay, so let me get this one back to the beginning here. And while I'm at it, I might as well see if I can do the same thing with that one there. That's the wrong way. This is the right way, or backwards way. So we'll have a clean slate here to start with the algebra. As you can see, it's somewhat formidable, all right? And there's some things that it's worth knowing about how you do derivatives and vector derivatives in particular with this particular Lagrange equation that we're going to get for electromagnetic field, with an emphasis on the magnetism, because that's the new guy in town here. So these are basically Maxwell's equations. That's really all you need. You get all the Maxwell equations just out of the potential scalar and vector with that, and everything kind of follows from. These are the drivers, you might say, of electromagnetic motion, and it's a good idea to get familiar with that as much as possible. So this is the F equal ma, the Newton 2 equation, written in the form that you have a V cross B being the curl of A, and then we have our good old minus, that's the Fayetteville minus. We don't have a minus for that, we have a minus here though, and that's very important because these two objects make a 4-vector for relativity later on, so this minus sign is to be respected. And then this partial derivative of A with respect to t, that's something that comes on in a very important way later on. Okay, so let's get those guys up there and a little bit more. The thing that I want to waste a little bit of time with, but it's not a waste of time. I think a lot of people have trouble with this. If you've learned your electromagnetism from Jackson, you've probably already done some of this because he uses both notation, the Gibbs notation with the fat letters, and then something that involves their components. And then you end up with a cross product being described by something called the Levi-Civita tensor, the anti-symmetric tensor, epsilon I, J, and K. A third-rank tensor, and it's a beginning of what we call exterior calculus. That's what comes out of vector and tensor analysis, something we would like to do in this class, but we just don't have time. I've tried it several times. It's going to have to be pushed off to when you do gravity. Okay, and then you'll be working with these things all the time. 1 forms, 2 forms, and 3 forms, all that kind of stuff. But this is as close as we get to that. In order to make this triple cross here, how do you handle a triple cross? It involves a differential operator, but also it's not trivial just to have another vector there of an ordinary kind. So you have the idea first that when you do a cross product, it's anti-symmetric. We didn't have to worry about that when we were doing the complex 2-dimensional vector potential. It was just very much a cousin to the scalar, but now this guy's got 3 components, and you get 4 altogether to worry about, but right now we're just worrying about the 3. So here we have a repeated sum here, epsilon K matches the K on this side. So I'm looking at the kth component of the triple cross, and I'm asking you to sum over three numbers, that is x, y, and z, for first I. Okay, so this I right here goes with that one right there, and then the J goes with the cross product, which itself, and here's a raw cross product of an operator, and we're going to write it as the A component of a little partial, because that's what the gradient has as a component. So there's three components for that and for that that we can make. So this is kind of a funny tensor with 9 components, 3 times 3, and they are all being summed. The A and the A and the B are being summed because they're repeated. Remember that thing about the dummy sum, dummy index row. Okay, so that is what we are going to be playing with, and I want to. And it's something you should practice on. It's not, if you're not familiar with this, you need to do some a little bit on your own, study on your own, to do this kind of algebra. That's what we're really after here. Now, what we're going to apply, since these two epsilons are sitting here in this equation, this one's summing over A and B, but it's also summing over the J right there, and then these two, the K and the I, are doing a sum as well. The I is anyway, and then the K belongs to the other side of the equation. But turning this into that is a key step. This is the Levi-Civita. I think I'm pronouncing it pretty close to that. Epsilon identity. The idea is that you're going to get 0 most of the time, and that's because this symbol, this thing, is sort of the opposite of the delta function. Whenever any two indices are equal, you're out of business. If any pair are equal, it just takes one pair, you're dead. So this tensor is pretty non-existent. It's only equal to +1 if you have an even permutation of 1, 2, and 3, basically, or x, y, and z. If you've got an odd permutation, it changes sign. So anytime you flip any two indices on this thing, you change its sign. So here are all 6 permutations of 3 things. 3 factorial permutations, 1, 2, 3. They're all even. 4, 5, and 6 are odd. So this is something that will take you not just in 3 space like we're working with here, but it'll be good for 4 dimensions, 5, 10, you name it. Go to the fancy Lie algebras. This guy's going to pop up. So we turn this thing into, and what you do is you just say, okay, I'm going to take the first 2 indices, K. I'm going to be taking the index I sum over here, and then I have Ki and AB kind of left over. Okay, so the basic idea is that you get a plus if it's Ka and IB, but you get a minus if it's KB and IA. The only other possibility for this product to give you something that's not 0. So that's it. If you can just do that trick, then you don't have to pull your hair out trying to figure out what things like that are going to be. It is a good path to be aware of. Okay, and of course these exterior calculus things get much more complicated than what we're looking at right now. So then I go ahead and I put the 2 terms shown individually, okay, and once you've done that, you just reorganize, and that's what you get. You get this particular combination. In general, okay, and then you can rewrite it a number of different ways, but this is an alternative to remembering a lot of things that Gibbs. Gibbs is this guy, he's an American physicist at Yale, and he decides that America's ignorant and he's got to learn what's really going on in Europe, so he goes to Europe. we'll tell more about what he found and later on as we discuss spinors or quaternions. That's what we'll really be doing when we talk about resonance, which is the next unit. And while I'm on that topic, I'm going to point out that I'm going to leave out a lecture. I'm going to leave out the lecture on constraints. I'm not going to give it. You're going to self-study that one. And there'll be a couple of simple problems to go with that. But what we're trying to do is get ahead so we can do some more connection to relativity and quantum mechanics at the end of this. So I'm cutting down on some of the things that are pretty obvious. The constraints stuff is pretty obvious. Anyway, Gibbs is the guy that discovered spinors. He came from America. He discovered what had been done by Hamilton, and then he brought it back. And that's where you get the I, J, and K notation in your calculus book, is from Gibbs, talking to or seeing Hamilton's work. Okay, but there is a little caveat that goes with all of these triple cross businesses, and that is Newtonian mechanics, and that's what we're doing here, but also the Hamilton mechanics that we'll get to in just a bit. We are going to say that the partial derivative with respect to a coordinate k of velocity j for any k and j is identically zero. Those are independent variables for mechanics. So we're going to be leaving out this thing from this particular combination. That is a key thing. The gradient of v is identically zero. Now later on you make a field or something like that and give up on the mechanics, you're just studying the things in a raw form, then this not necessarily be something you would write. But for mechanics, it is. And so this is a real sticking point. This business of dependency and dependency of independent. We in mechanics, we pick initial condition, that's a position, and then we put an arrow on that, that's the initial velocity, right? And you can choose those anything you want, right? So they're not related by a derivative formula. Okay, that key idea I really want to emphasize. So we got a big zero right here, okay? But you would normally have a little bit more if you did that. You'd have a gradient v in there. So this gets thrown out. Okay, to do what we're going to do, which is mechanics, we have to take that step for sure. Okay? All right. Now, let's go through the algebra that we get after we've done that. This index notation really helps you to distinguish between, say, something that's a gradient of a, all those different things. You just write them out as components. Everything has an index. So you make tensors and vectors out of everything in a notational way. So that, and then we say, okay, Gibbs, you've got nice shorthand, but it screws you sometimes. So we're doing the stuff that's on the second line there. Okay? And that is, I think, what we really be thankful for this particular thing that we're about to do here. Okay? All right. Let's go ahead and do it. So this is the thing that this turned into. There's two terms, but boy, they're important terms. And we've got to make sure that they behave and do what we can. So here's writing it out. There's a chain rule. Write those guys out as a chain rule. That is, we're really talking about now a total time derivative of A. So that's going to be a partial with respect to x of whatever x velocity you have, a partial with respect to y, whatever y, same for z. Okay, so we've got three terms right there. Plus, now we really have to take into account an explicit time dependence for A, because that's the laser. The laser is going to be coming in wiggling at some 700 terahertz or something like that. So you got a big time derivative for almost all electromagnetic problems that we do in quantum optics or whatever. So we basically have a v dot grad A it's sort of a flow term right there, if you will, and then the partial A with respect to time. So this is very much a mechanics of things that are coming from the outside and making havoc out of the life of for a molecule or atom, which we then use as a computer maybe someday. But here's the mass times acceleration in its usual form. Move this guy over here so I have the gradients next to each other, and then I have this little partial, and then a v dot gray, the flowing term, for the time behavior of this thing. Okay, and then we put them together in another way. Okay, so here's kind of where we stand just with respect to doing chain rules to get these Gibbs fat vector notation into shape. Now I start pulling the things apart a little bit here. Basically, I'm pointing out that what we're talking about here, remember when we did our Lagrangian, we were thinking about partials with respect to velocity, the time derivative of that, and it was a partial with respect to velocity of kinetic energy, mv squared. This is three-dimensional kinetic energy of a particle of mass m. Okay. So I'm pulling out of this thing also the time derivative. That's the total time derivative of this. Now, this equation here is pretty obvious, but there's also the fact that now I can deal directly with this term right here. I put the charge onto the EA and put it aside, and then get these gradient guys organized here, okay, as they are, okay, and then from the other part of this, the total derivative, remember, we're talking about derivative of A, and then we've got the flowing part right there. So eventually, the whole idea of this is to put it together in a form that represents or resembles the Lagrangian equations. This is where you sort of sit there and scratch your head and figure out how do I make this into something that behaves like the Lagrangian equations. So first thing to do is notice that I can write this whole thing just as a partial with respect to the coordinate vector r. That's a gradient, but I'm rewriting it, okay? And I've got here the kinetic energy, and then I've got here this thing that has a potential in it, but also has a vector potential multiplied by the velocity, and that's the trick right there. This is in the form now of a Lagrangian equation. Let me go ahead and just write the thing here, and then you see, voila, okay, abracadabra, we have made here a Lagrangian equation. We have a Lagrangian now. We have something, this thing, that behaves like that. Okay. Now, this step here requires that we make use of that formula that says that r is an independent variable of velocity. So, you know, that it allows us to put it here, but it's not doing anything. It's giving 0. And that's a pretty neat trick right there. Okay, let's see if, anything else I can say. There at the very bottom of that screen is what we're after. Okay, bottom line. This is the bottom line for the derivation of the electromagnetic Lagrangian and Hamiltonian in a minute, and I'll put all that stuff together and see if we get Maxwell's equations, basically, from that. Okay? All right. So, canonical momentum. What the heck is that? Canonical means that Pope is right. But what's the Pope doing here? Nothing. We've got to use old-fashioned notation for this business. We've called the momentum canonical a few times in this class. Now, well, maybe we kind of mean it. Okay. This is what happens. Somehow, the momentum, and that is the part of the motion that has to do with mass moving, gets mixed up with this guy, this vector potential, this flow associated with the vector potential somehow gets entangled or something with the stuff that we're kind of used to as just particle momentum. So we're really used to this, but what we're saying here is that the P that I've got here is this. It's MV all right, but you got to add this thing in order to make it work. Well, that's what Lagrange tells you. That's basically what happens when I take the partial with respect to V of the thing that gave us Lagrange's equation. So this is the bona fide momentum that we're going to have to deal with if we're going to get right with light. Okay, that's what we're doing here. We're getting right with light. We're getting electromagnetic wave phenomena to show us something, but also static B and E fields as well. But this is going to be good for relativistic quantum mechanics, basically. The same darn thing you do for it, we're doing here. Okay. So, this just says, if I don't have any A field that I have to worry about, then momentum is what you're used to. But here, and boy, they're always sawing wood around here. I guess it's wintertime, we're getting the logs stacked up somewhere. But anyway, this Lagrangian form, the usual form, L equal T minus V with electric potential. But if there's a magnetic activity around anywhere, then you really do have to take account of everything that we've written down here. And I'm going to go ahead and just finish this one and talk about what it is that we can call these things that we're writing down here. Okay. A naught 0, this leads to what I would call extraordinary canonical momentum. That is, P is mv plus VA. Okay, now, I'm going to go ahead and solve that and say, well, if you want the particle momentum, that's the particle momentum, no question about that. Then you take the canonical momentum and you subtract the A. That's just the arithmetic that this is giving. So that's what we're going to have to do to make a Hamiltonian. In order to make a Hamiltonian, we're going to have to stick that into the Lagrangian transformation, that is the Legendre transformation that takes us from the Lagrangian, that is this very beautiful thing that we worked on almost in the first week or so, where we have a V dot P. Well, in our notation, after we get tensorized, is the queer coordinates dot, and then the queer momentum. Okay, this is a sum. I'm putting a sigma here just to remind you that the dummy sum rule isn't always used in literature. But when I go here and do a V dot P, now there's P with the A that goes along with it now, and then we subtract the whole Lagrangian from that. That's the Legendre transformation from the Lagrangian to the Hamiltonian. But look what happens here. V dot A cancels the minus V dot A. What? The Hamiltonian is just a scalar. The only thing left is a scalar. This sounds really crazy. What happened to the vector potential? Well, it's around, but it's not here. This is only correct numerically. This is a numerically correct equation. Like when we've done this transformation before, right? We got something that's kind of weird. But we're going to change that now and get it in terms of momentum, canonical momentum, and then we'll be off to the races as far as Hamilton's concerned. But still, we have this thing as a numerically correct equation. So we do have to go ahead and say a few words about that. But the basic idea is to replace the Hamiltonian has to be an explicit function of this momentum that we had written down before. So we're going to stick that in there. That is definitely what has to happen. V dot V is going to be this P minus EA, electric field, electric charge A on the thing, and then we're going to get what we're really after here, which is a Hamiltonian that supposedly will work, whatever problem you do. So if you're going to do quantum mechanics, it's much harder to build Lagrangians than it is the Hamiltonian. Hamiltonian kind of wins at first here, and this is numerically and formally and differentially correct. And so you're going to be seeing momentum dot A's, and you have to be careful. You're going to use this for quantum mechanics. You have to realize that A has R in it, that's position, so I've got to keep the order here because X and P don't commute if I'm going to do quantum mechanics. But we're not classical, so I'm just going to mix them up and get rid of the 2 here. But be aware that is in the cards. Okay, so question is, what do Hamilton's equations look like given this Hamiltonian? Okay, we know what Hamilton's equations look like. We're just going to see if they give us something that makes sense. And that's the rest of this algebra here. Well, the first one isn't too tough. This one, at first you say, well, didn't I see this before? Isn't this what velocity came out to be? Yes, it's P minus E over A divided by A. Okay, you take a partial derivative of this thing with respect to P, and that's what you get. Okay, so this is Hamilton's second equation here. Now there's, am I right in saying that? Yeah. Yes, I think so. So, the basic idea is this just copies what we already know, or what we had to assume in order to make this work. Okay, so that's a key point here. But now we better get Maxwell's equations. We've got some more Hamilton equations to deal with. This thing that we've just written down in index notation anyway is the Hamilton's dp dt equation. Okay. So now here, this is P dot now. This was R dot. This is the P dot equation. It has a minus sign in it. You check all this on the wall on the Hamilton section up there. Okay, the partial derivative, that's the first equation. H with respect to the momentum is velocity, and H with respect to the velocity is minus the momentum dot. Okay, so what we just did, well, this is a bit of a mess at first, but it works out pretty nicely. We have to be careful to do the derivatives, and we're working in component form. Doing this thing with Gibbs notation will make you bald by ripping your hair out. You'll not get very far with Gibbs, but this is going to work. This thing right here is just a component B. This thing we recognize as the partial A extra electric field combination. So what we will find after we've put all this together, and of course we've had this equation already, and then we can keep this going on the other screens here. I'll go ahead and take it to that point. And notice there's a cancellation of A dot. That is really key. That's very important. So you can make a sign error, not have that happen, and you'll get a mess. But what you're getting now is this. And guess what that is? That's just mv dot equals, what the heck is that? Well, that's v cross p plus e. That's ma. That's the Newton's equations written out using the proper notation. Okay. So we've come full circle here, back to the equations that started that. The name for something that tells you how a velocity of a mass behaves is called a ponderomotive equation. I mean, it just means push the mass. This thing right there is the basic definition of the force equal mass times acceleration. So that's virtually it for getting Lagrange and the Hamiltonian and checking them out. Okay? All right, we're going to apply this now. The first thing that I want to do is get the FBI rule out and get it exposed. But we'll do the very simplest possible electrodynamic mechanics here. We're going to have a constant E field. That means there'll be a scalar potential field, constant gradient. Okay, that will be the thing that we'll put down first. And let's get that up here and up here. Try to keep these boards sync because we're going to have times when we compare some things. And this will be the thing after we talk about the effect of the A, that's the thing that builds the B field, if you're thinking of going from potential to field. This is a rigid, this is a field that I had to do a problem with. It had involved the water being rigid. This A right here is going to be the velocity field on this mechanical envelope. I mean, that's how crazy this is. But it isn't really so crazy if you think about it for a while, because the A field that you get, if you have a constant B field, is just B cross R over 2. Okay? So that's why this rigid rotor field corresponds to the vector potential. You actually have the vector potential exposing itself in an analog, mechanical analog. And then there's going to be balls that roll on this thing without slipping and behave like a particle in a cyclotron. All right? Did you, when you came to class today, did you think you were going to see something as weird as this? I mean, this is weird. Okay? But vector potential is weird. We're used to scalar potential. It's kind of weird too. But vector potential is what you get if you have a scalar potential and you run through it relativistically. All of a sudden you're going to see A. And it's going to do stuff like this. Okay, so that's what we want to talk about. This is the simplest possible thing involving those. And I'm not having any explicit time dependence of this, but we're next unit, Unit 4, which will start on Monday, is resonance. And cyclotron resonance is why you make a cyclotron, to accelerate particles. It was the first particle accelerator. It's a thing that this is analogous to. Okay. So the equations of motion we have here are quite simple. Well, not simple enough that they're obvious ways to make a solution. What I want to do is use a shorthand notation for these. First of all, that's the first thing. Get the notation so it's fairly clean, and I don't have to drag the electric charge and the mass around in every equation I write, because we're going to be writing lots of these things over and over again. So I'm going to have a little epsilon x and an epsilon y that means E over m, that famous ratio, the Thomson ratio, I think it's called electric charge over mass. That's going to set the units that we're talking about here, that times the electric field. And we're going to use the same one on the B field. And the B field is going to be all in the z direction, making this rotor, and the electric field is going to be crossed with it, that is perpendicular to it. And we'll just take the x field eventually. And that's all that machine can provide. It can make a table go like this. I have not been able to put something that would make a table go like that in there. You'll see why I didn't do that, because it's really hard to control. Anyway, So the Gibbs notation would be something like this. And once again, I want to get away from Gibbs notation. I want to have a simple way to manipulate these equations, see what they're doing, and you know, make the physics understandable as much as possible. Okay? And that's where you bring in complex variables. This is why I made a fuss. One of the reasons I made a big fuss about complex variables in the Unit 1, Chapter 10. So let's get all of the boards reading what we're after here. So when I take a complex variable velocity, all I'm going to do is make it complex by putting just one as a component in front of this x component, and then an I in front of the y component. So I'm going to be writing each of my two-component things as a single number, which is a two-component thing. It's got a real part and it's got an imaginary part. And we're going to play that game. We're going to go ahead and write the equation of motion that way. That is, we're going to have an x component of the velocity dot, that's an acceleration in the x direction, and then this is the acceleration in the y direction, being carried a single complex number in each case. So you see the velocity there, and then you've got the electric field right there, and then you've got the b number on top of that. So this right here, this cross product is giving you a Vx Ey, that's unit vector y, and this is a Vy unit vector x. Okay, so how does the complex take care of that? Well, it just puts the I, a minus I on this one, and changes the, in other words, basically this has to go down here if it's going to be in the place where you normally put the imaginary part. In any case, this is the b, that's a real number, times a complex number v. This is a complex number E for the electric field, and there's the velocity dot. So this is the equation we're working with now. That's simpler, right? We can take derivatives and integrals of that thing until you're blue in the face, and it's easy to write them all out. So that's what we're after here, okay? So it's a velocity transformation that I find really useful is to call something a big V if I add a number beta, which I can control. And we'll see how that works. But the beta that I'm going to be adding to it is an imaginary number, the ratio of the electric field to the B field.